One thing you'll notice about this slide set, it's completely different than the others. The one that was provided by the the publishers that I tend to take and modify just wasn't worth dealing with. So I went back and pulled this one out. This one was gifted to me by my predecessor. Dr. John Dynack was in my position before. And when they brought me on as an adjunct, and then actually as a visiting, he gifted me his whole slide sets so that I could teach this course over here while he taught over at Greenbrier. He's since passed away, but I kept his slides. Can't take them with you. Okay. Before we get into that, let's ask the question, why gases? What's so special about gases that they deserve a whole chapter by themselves? I like to look at it from a historical perspective. When science was emerging from the Middle Ages, alchemists and later early natural philosophers, they call themselves, were fairly proficient at manipulating gases. And they had devices, they had the technology to deal with gases on a limited scale. But the unique thing about a gas versus working with liquids and solids is that for many of the rules or laws governing gases, it doesn't matter what gas you have. One gas is good as another. So, oh, there's Xavier. Let me break for a second. Xavier, the class has decided to meet Thursday, the 25th, between 9 and 12 for a tutoring session. Since we're going to have class that day anyway, I'm going to meet here in the classroom, and I'll be Zooming that session so we can record it. So if that's a problem, then the majority rules.
No, that's fine.
That's fine? Good deal.
Yeah.
Okay, so back to gases. So then if gases were historically important and easier to manipulate and well-behaved in terms of some of their physical properties, and we're going to investigate those in just a minute. Why are they that way? Gases are very, they have very low density. In other words, very few particles as compared to liquids and solids, very few particles per cubic meter. So they behave as if the particles aren't even there. And that's the way we treat them, ideally. The particles that are there, we count them as reasonably independent. We say semi-independent just to cover all our bases. Because when two gas molecules approach one another, ideally, we treat them as if they're billiard balls. They just bounce off each other. We know that there are sometimes repulsions and attractions, but we deal with that later. We're going to treat them as ideal in the beginning. And under most circumstances, we can treat them as ideal. So we know that gases are very rapidly moving particles, and naturally, why do we know that? Because most gases are at relatively high temperatures. Right? A few gases are still gases at low temperature, but we're going to explain why that happens also. Now, we know they're rapidly moving now because we can measure it. Right? But in the beginning, we had to just assume that they were that. Rapidly moving atoms or molecules. Now, this is true. This has always been true. Gases are completely miscible in one another. That is, when you put two or more gases together, you always get a homogeneous mixture or a solution, right? And just take a deep breath and you've got a solution of nitrogen, oxygen, some argon, and some other minor components. Now, gases, they do have mass. We can measure their mass. In fact, one of the labs that we're going to do this year, we're going to measure the mass of a gas so that we can determine its molar mass. So gases do have mass. That means the particles, the individual particles have mass. We know that they're there. They're physically there. And they possess kinetic energy because we can measure a temperature. Temperature is an expression of the average kinetic energy of all the particles in a substance. Now, this idea of random motion is out of necessity. Even though gases are really thin, this sample of gas still has billions of molecules in it. Right? We can't track every one of them. So we treat them statistically. They're random motion. In other words, we can't tell where they are. They could be anywhere. So we're going to look at things like how the gas laws work and how we can combine them, how we can interact them to describe a gas in physical terms. That's what the gas laws do. But we're also going to use the gas laws eventually to understand the chemistry with gases. We treat them as ideal. In other words, an ideal gas acts as if the particles aren't even there. And another way of saying that is we can cool and compress a gas right down to nothing. It stays a gas all the way down to absolute zero. That's ideal behavior. Now, we know that's not true. Right, we'll talk about that later. We're going to solve problems with the gas equations. Now, just as an example, I mentioned the solution of gases that we breathe every day, primarily nitrogen and oxygen. They're necessary for life. Now, the oxygen we know is necessary for us as heterotrophs. We need oxygen to metabolize stored energy of whatever kind, carbohydrates, fats and oils, proteins, nucleic acids. We need oxygen to break them down and extract energy from them. So they are necessary for life. But for autotrophs, like green plants, oxygen is a waste product. So what those plants do is they take sunlight as their energy source and they build molecules using carbon dioxide and water. So for plants, carbon dioxide is food. It's not a pollutant, as the EPA wanted to say not too long ago. But as so often is true with the EPA, they were wrong. Now, there are some bona fide atmospheric pollutants in this solution that we breathe. Some places are worse than others. Like Los Angeles, for instance, when they get a temperature inversion, you get heavy smog because they're burning a lot of fossil fuels, automobiles, and they produce oxides of nitrogen. And when you get a temperature inversion, that is the warm is underneath the cold. So the cold traps the warm in there, and that keeps all those pollutants there until they get a rainstorm or a breeze from the ocean or something to drive it out. Then it cleans things out for them. But those pollutants stick around, and they're not good for you. Oh, by the way, you guys are probably too young to remember the original laser printers. The IBM laser printers were like that wide and that tall. They were monsters. One of the things they found that they produced, those little lasers in there produced, was ozone in significant quantities. So until they figured out how to stop their printers from producing so much ozone, they stuck little bags of activated charcoal in there inside their printers to absorb the ozone. So if you ever see one of those old printers, like in a flea market or something, crack it open and see if they've still got one of those bags in there. But you can get pollutants from a lot of places. Let's see. That thing is shifting around too much. Now, don't get me started on global warming. The first time I heard that expression, man-caused or anthropogenic global climate change now, because warming doesn't work anymore, because the Earth's getting colder sometimes and warmer some other times. So they had to change their tactics to global climate change. First time I heard that expression, I didn't believe it, and my opinion hadn't changed. In fact, now there's ample evidence to show that all the 20 some odd models that they use to predict temperature changes, none of them work. They all fail. Not even with the massive tweaking that they do, because the climate, Earth's climate, is too complex. You just can't model it efficiently. And the scientists who have half a brain and are actually working on the problem, they tend to ignore them. So I'll let it go at that for now. Okay. When we describe a gas, and this is any gas, we need 4 parameters, 4 variables. We need to be able to describe that gas in terms of its pressure, in terms of its volume, in terms of its temperature, and how much of it is there. That little n is my abbreviation for moles. Okay. So if we know these 4 factors, we can completely describe the physical behavior of a gas. All right, first, pressure. How do we define pressure? Well, pressure, by definition, is force applied over an area. So in SI units, a force is in newtons, right, abbreviated N. Newtons per square meter would be the standard of measure for pressure. But historically speaking, it was difficult to make assessments of gas pressure using this formula. This is what we go by now, so that we can convert from one unit to another. Like if we have the fundamental unit for area is the square meter, because the fundamental unit of length is the meter. And then the Newton is a derived unit. It's derived from Newton's second law of motion. I don't know if you've ever seen that. If you haven't had physics or physical science, you've never seen that. Newton's second law of motion simply says if you have a mass of any size and you apply a force to it, you'll get an acceleration. That is a change in velocity uniform over time. So if we say mass is a standard measure of mass is a kilogram, an acceleration would be meters per second squared. Meters per second is velocity. We're changing velocity, so it's meters per second per second. Right, so acceleration would be meters per second squared. So this value over here, this Newton, 1 Newton is equal to 1 kilogram per meter per second squared. So the reason I tell you that is because if you start to do calculations and you need to know what a unit is made of so that you can assess, do your dimensional analysis, cancel units, combine units, you need to know what they mean. So this Newton is a valid measure of force, but it also means that. So if you have it in an equation where you've got kilograms and meters and seconds, part of the other units of the other variables, then you need to use this one so that you can combine or cancel. Okay, that's the only reason I showed you that. You don't have to memorize that, except to know that this is what it means. Okay, so that's the formal definition of pressure. Historically speaking, measuring gas pressure goes back to an Italian by the name of Evangelista Torricelli. 1643, he introduced his barometer. And barometer, meter just means measure. And baro means atmosphere. So he was measuring the atmosphere, measuring the pressure of gases in the atmosphere. And to do it, he needed a liquid because a solid wouldn't do, right? A solid would just sit there and do nothing. So liquid would respond to differences in pressure. He needed a liquid and he needed a glass tube that was closed at one end, like that. Okay. And in the middle 17th century, glass blowers were very good at producing uniform diameter tubing. So that was no problem. He could get one of those on any corner. Kind of like when I visit Rhode Island with my wife, there's a Dunkin' Donuts on every corner. Well, they had glass blowers on every corner in Italy. So he needed a liquid. And he reasoned that if he filled this tube up, right, this way with the open end up and closed it off, and then inverted it and submerged it in the liquid, then if there was no pressure here, if there was no gas pressure there, then that column would stay right where it is. But if there was, actually, that's not true. If there were no pressure here, it would drop all the way to this level. Okay. But if there were pressure on the outside, it would be transmitted. Pressure would be transmitted and it goes 3 dimensions, every direction. It would be transmitted here and the pressure would hold that column up at a certain height. That was his theory. So he created the device and he needed a liquid. I don't know if he really tried water, but pure water was available. You could get pure water. But maybe he reasoned by the density of water that he would need a tube that was 33 feet long, right? Minimum. And that wouldn't be practical. So the only other liquid that was a candidate was mercury, because it's a metal, very dense, like 13.5 times more dense than water. And that means his tube could be shorter. So he used mercury metal. And they didn't know about mercury poisoning back then. So he just put his thumb over it and dumped his hand in the mercury. Actually, liquid mercury like that is not extremely dangerous. If it vaporizes and you inhale it and it gets in there and stays there, then that's a problem. Or if microbes get hold of it and convert it into an organic form like dimethyl mercury, then it is extremely dangerous. I'll leave off with the horror stories for now. But you don't, if you're going to deal with that stuff, you want to be sure that you've got impermeable gloves, respirator, and all kinds of under a fume hood. Right. Anyway, so when he did that, it did drop down to here. Now, where he was located was probably above sea level. So it's going to drop down below. If this was 1 atmosphere at sea level, it would have dropped down a little bit if he were above sea level. So he put this in the back of his ox cart and went up a mountain and it went down. So he was confirming the fact that there was air pushing down, and the higher you go, the less air there is above you to push down on it. And then he went down to sea level and he found that it went back up to here. So it didn't take long for other scientists to adopt this instrument to measure atmospheric pressure. Oh, I do have an animation. So there you go. Is it going to go? atmospheric pressure. Now, the units of measure here, of course, and the concept of the meter and the centimeter and the millimeter were already established at this time. So all he had to do was mark off his tube in millimeters, and then he could measure the height. So we take 1 atmosphere now to be 760 millimeters of mercury. All right, and it doesn't matter how big this is or how small this is, it's going to be 760 millimeters at sea level on average. Okay, so is that an intensive or an extensive property? Intensive, because it doesn't matter how big it is, it doesn't matter how much you have, it's intensive. So that's one like temperature that is intensive without being a ratio. Okay. So by the way, when that mercury dropped, what do we call something when there's matter there 1 second and then there's no matter there the next second? It's a vacuum. So he produced the first vacuum up here. Now we know that mercury is very slightly volatile. So there are probably a few mercury atoms floating around up in there, but for most purposes, we can call it a vacuum. Okay. So he and other scientists were curious, how can we use this new device? Because it's pretty neat, right? We can measure air pressure with that. So some people took it below sea level, right? Some people just sat it on their desk and watched it over time, and they saw it fluctuate. And they began to associate the movement of that mercury with the weather. So when the weather, they see storm coming in, mercury would drop. And when it passed, the mercury would go back up. And we still use that concept today. High pressure, low pressure on any weather map is an expression of that phenomenon. Okay. Right, they used it to predict the weather. But how does that help us with gases? Because a gas has no definite volume, it's an indefinite volume and an indefinite shape. So it has to be confined, all 3 dimensions. It has to be confined in a container. Well, how do you measure the pressure of that gas if you can't get at it? Well, you have a device like this, only it's not exactly like that. In order to measure the gas inside a container, you need a manometer. So we do this, close it off like that. So now the atmosphere can only press here. Excuse me, we leave this open now. And we let the atmosphere press there. And we attach this to a container of gas. Okay, so now the pressure in here is due to the gas, but it's fighting, the pressure in there is fighting against the height of the mercury and the atmospheric pressure. So manometers are always open to the atmosphere. So what's the pressure inside there? Well, it's how much mercury it can elevate. So the height here, millimeters of mercury, plus atmospheric. So you need another one, a barometer over here, to tell you what the atmospheric pressure is, so you can add it to this height, and that's the pressure of the gas inside. So far, so good? Okay. That's a manometer. Now, if anybody's ever worked in a doctor's office, or some doctors still have them on their wall, they don't ever use them anymore. The mercury sphygmomanometers to measure blood pressure. So you have the cuff and you pump it up so that as your heart beats, it pushes against that cuff. And that cuff is attached to this, right? So it pushes with frequency of your heartbeat. And you can see this thing bump, 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 bump like that. Well, you pump it up and then you gradually release it. And you'll see it do things like that. And it'll get really strong for a little while as it goes through the systolic, and then it'll die away when it reaches the diastolic. Now, the way you tell when you've reached those points, it's more accurate to listen. So that's why the doctor or the nurse will put a stethoscope right there below the cuff, so they hear those sounds. Those are called the Korotkov sounds, and they're like 5 or 7 of them. But the ones they're really listening for, they're really strong when it first starts beating, is your systolic pressure. And then when it dies away, that's the diastolic. And they give you those two values. Like mine's usually 135/85 or 90. It's a little high. But it's been that way for years, so I guess my doctor's not too worried. So those are ways that this device can be used. Now for us, we're more interested in the manometer type. Okay, normal atmospheric is 760. Now, on this particular day, pressure of 694 millimeters of mercury was measured at the Raleigh County Airport. And at 2,504 feet above sea level, we should have, that's reasonable, right? It's a lot less than 760, which would be at sea level. So we're a half mile high, it ought to be low. So what's the pressure in atmospheres? Well, notice we have an equivalence here. Whenever you have an equivalence, you got a conversion factor. So if we're starting at 694 millimeters, and we want to convert it to atmospheres, we need a conversion factor that will cancel mercury and leave us with atmospheres, right? So here we have 1 atmosphere is 760 millimeters of mercury. So we just divide 760 into 694 and we get something less than 1 atmosphere. So this is what it would look like in my animation. 0.913 atmospheres at the, and that's their, see, what do they call that? Airport code, some kind of code. There's always a 3-letter code. BKW is Beckley Airport. What's Charleston? I can't remember that one. I know Atlanta is ATL. If we went higher, another 1,000 feet, on that same day, we'd get 669 millimeters of mercury, so it should be less than 0.91, and we do the calculations. And Winter Place is just up the road, right, where they go skiing. 0.88 atmospheres. Now, I'm not sure what the physiological limit is. They usually pressurize airplanes at what, 10,000 feet? That's why your ears pop when you go to altitude in a jet. And they only pressurize them at the lowest pressure possible for the comfort of the passengers, because whenever you pressurize the inside of a plane at those altitudes, it expands. And then when you come down to land, it contracts. And it just does this, bellows, every time you go up and down. And that stresses the frame, and eventually you develop cracks. And at that point, the plane is grounded until they fix it. Hopefully, they catch it before it blows a side panel out and sucks passengers out into the void. Like, what was that movie? World War Z with Brad Pitt. Set off a grenade and it sucked people out. Now, that could happen. I don't think it would happen at that altitude, though. They were too low. But it was a nice effect. Okay, so if we have 1.032 atmospheres, now we're going the other direction. But we use the same conversion factor, only now we flip it, because we want to get rid of the atmospheres and give us millimeters of mercury. Right? And we can do that because all conversion factors are equal to 1, right? The ratio equals 1. So that's why you can flip it whenever you need to, because it's going to be 1 either way. Use your conversion factor. Okay. Now, as far as I go back to that original definition of pressure, if we have a Newton per square meter, that's given a new value called the Pascal. And this is a derived unit. So it's a derived unit from a derived unit, right? Newton is a derived unit. Pascal is a derived unit from Newton per square meter. Pascal's named after a polymath, a Frenchman in the 1700s, I think. He was good at a lot of stuff. Have you ever heard of Pascal's triangle in math? You may have seen it before. Let's see, 1, 2, 1. You just add these two together and that gives you this one. Right? Add these two together, gives you 3, 3, and 1. 1's always on the outsides, 4, 6, and oops, 4, 1. It just keeps progressing and getting bigger as you go, kind of like bowling pins. It's Pascal's triangle. Okay. So gas pressure is one of those concepts, those variables that has lots of different units available for expressing pressure. In the beginning, we're going to use atmospheres. It's just more convenient. But suppose we have a device that doesn't measure in atmospheres. Like the barometer in the lab measures in inches of mercury. So 1 atmosphere, let's see, let's put our units up here. 1 atmosphere is equal to 760 millimeters of mercury. It's also equal to 2992 inches of mercury. Okay. It's also equal to 14.69 pounds per square inch, PSI. Okay. Now this one is a ratio, pounds per square inch. That was not a ratio, that was not a ratio, and that was not a ratio. But they're all intensive properties, expressions of the same intensive property, pressure. So when we do our Boyle's Law experiment, when, let's see, when are we going to do that? I think it's next Tuesday. Yeah, 23rd. We're going to do Boyle's Law. We're going to measure pressure using a tire gauge. And a tire gauge is going to be in PSI. So we got to be able to convert PSI to atmospheres. And we're going to measure the atmospheric pressure in inches of mercury. We got to convert that into atmospheres. Because remember what I said earlier, if you want the pressure inside the vessel, you got to measure the pressure inside the vessel plus what's pushing on it from the outside. So we have to add the measured pressure plus the atmospheric pressure. And they both have to be in the same units, right? We're going to add apples and apples, not apples and oranges and lemons. Okay. All right. And sometimes you'll see weather maps are the recordings of pressures on weather maps are in millibars. So a bar is 100,000 pascals. A millibar would be 1,000th of that. So a millibar would be 100 pascals, right? 1,000th of that. 1013 millibars is equal to 1 atmosphere. Okay. Weather maps. We don't do weather maps in this class. I do it in my physical science class. And if we want to convert to pascals, we got this other value, 101,325 pascals is equal to 1 atmosphere. Now these values, let's see, in your review document, useful information, all these values should be, yeah, there. Yep, they're all there in useful information. And what does that mean? That means on the exam, they'll be there too. You just have to know how to use them. That's where solving problems comes in. Okay. So, if we converted 14.45 psi to atmospheres, that would be the conversion factor, because this equals that. That's an equivalence. We can make a conversion factor. But we want to go to inches of mercury. All right, so now that we've got it in terms of atmospheres, we can convert atmospheres to inches of mercury. So now we have a different conversion factor with those two. This is a chained conversion. Think back to was it chapter 2, I think. Chain conversion. So 14.45 psi equals 29.43 inches of mercury. Different units, exactly the same phenomenon. The mercury's at the same height, it didn't move. We're just expressing it in different units. Okay, millimeters of mercury to millibars. All right, going to convert it to atmospheres and then take the atmosphere relationship of millibars and convert that. So 957.3 millibars. All right. I'm not going to spend time on this. This is just a justification for the expression of millimeters of mercury and converted to pascals. And we're using the density of mercury at 13.59 grams per cubic centimeter and the volume inside the tube, if it's a 5 millimeter diameter. And that just shows you that this is a valid expression. You don't have to know any of that. I just threw it in there and I never got rid of it because it took so long to create it. It's there for posterity. Okay, now we're going to talk about gas laws. And the first one we're going to talk about is one where pressure is related to volume. This is Boyle's law. What time is it? Okay, I got a half hour. If I really got a long way to go, then I'll stop. And I built in a buffer day, I think. Yeah, Tuesday I built in a buffer day. So we can finish it on Tuesday. Robert Boyle, and these laws, we're going to take these laws in roughly chronological order. And the reason we're doing that is because the technology that's required to express, to manage these variables is dependent upon the available technology of the day. And at this time, during Robert Boyle's life, during the mid-17th century, they were pretty competent now with Torricelli's measuring device of accessing this variable and that variable. They knew about these two, I think. No, they didn't know about this one. They didn't know exactly about this one, that the expression of moles. They just knew that there was amount of gas. And they could measure masses of gas. So they knew that was possible variable. And they needed to hold these. In other words, if you're going to use these two in Boyle's law, then these have to be constant. Okay. You're going to compare any two of them, the other two have to be constant. So how do we make temperature constant? Well, one way is just the experiment takes about 5 minutes, right? And moles, you just be sure that the gas that you've trapped to measure pressure and volume, you don't add any to it or you don't subtract any from it. Okay, there are no chemical reactions in there. There's no way for the gas to get in and out. Then you're safe with these two. Okay, Boyle's law simply states pressure times volume is a constant at a constant temperature and a constant amount. Now, the way Boyle did it was he modified the barometer. Instead of a straight tube, he made a J tube. I think I got a picture of it down here somewhere. Let's go to the next page. Maybe it's over here. Oh, no, it isn't. Okay, go back. We'll describe the J tube first. So he took that tube that was closed at one end, like that, and opened at this end, and he poured mercury into it. So I poured a little bit of mercury in here, and it cooled up on the bottom. They poured a little bit more and pulled up some more. When he pulled it up till it touches the inside of the curve, now all this gas is trapped. That means we're at fixed moles. No more gas can get in or out. So he just kept pouring, right? And he noticed that as he poured more and more, the levels didn't match up, right? So if we measure the difference between, say, this one and this one, that height is a measure of the difference in pressure from here, and here, right? This height of mercury. So let's say, just for argument's sake, it's like, I don't know, 25 millimeters of mercury, okay? So he took these measurements, these differences in these heights, and he put these measurements and used that height as an expression of volume because the diameter of the tube was uniform, right? So what's the volume of a cylinder, right? Height times area. So if the area is constant, then you can express the volume in terms of height. So that's what he did. And he compared the height of the mercury to this height right here. We'll call that L for length. So this actually, that should be L and this should be H, because that's an expression of volume. So this is the volume of that. And the difference here is this 25 millimeters of mercury, but what's the total pressure? Total pressure is that plus whatever the atmosphere is. Right. So that's total pressure. So total pressure versus the height, or in our terms these days, it's volume. Pressure times volume is always a constant. Right. So when he graphed it, right, Boyle knew about drawing graphs back then. Right? It wasn't something we invented just for this class to torture you guys. So what's the independent variable? Who's changing what? Boyle changed the pressure by adding mercury, right? So it's going to be on this right here. And nowadays we call it atmospheres. And the response, the dependent variable is volume. And the fundamental unit is liters. So we just put liters up there. Okay. He probably used something different, but for our purposes, that makes more sense. So what he noticed was at low pressure, you have this high volume. And as you increase the pressure, the volume went down. And it just kept going down, 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 down. So you increase the pressure. So our best fit curve would look something like that. Okay. And a modern expression of that would be also giving you the pressure times volume values, and these are theoretical data. So the P times V is going to be exact. If you did this experiment in the lab, it would be more variable. Okay. So if you remember from math class, what does that look like? In math class, you probably had it expressed like this. Have a mirror image over here. Does that ring a bell? Hyperbola. That's a hyperbola. One characteristic of the hyperbola is these tails never touch the axis. They'll go on forever and never touch the axis. And think about it, it just makes sense. Can the pressure get so high that the volume would get low enough so it would touch the axis? If volume touched that axis, what would it be? It would be zero, right? And then your relationship falls apart. So it has to be a non-zero number. So it just gets smaller and smaller and smaller, and this one gets bigger and bigger and bigger. So that's characteristic of a hyperbola in the real world, not the math world. Okay. So that's what Boyle did. And he maintained constant pressure simply by conducting the experiment over a very short period of time. But he wasn't able to, unless he did the experiments very close together, just like in sequence, he couldn't compare the data from one to another because the temperature might vary over a long period of time. So it's only good for that one expression. Now, that one set of conditions. This is known as an inversely proportional relationship. Inverse proportion. And we got that snoot full of that in the graphics lab, right? Inverse versus direct. So if the inverse proportion is with the variables, if their products equal a constant, if one goes up, the other one has to go down. That's an inverse relationship. Okay. All right. And that's going to be characteristic of any product of two variables equal to a constant will always give you an inverse proportion. Now, what we're getting to now is how to use these to solve problems. If you've got conditions, starting conditions, that we have a value here and a value here, we know what that value is. Like if we said this was 5 and this was 20, right? This would be atmospheres and this would be liters. And K would have to be what? 100 liter atmospheres, right? Whatever you do to the numbers, you do to the units. So we can't cancel them. That means they have to be liters times atmospheres. That's what the unit is, liter atmospheres. Well, if we change the value, see, this is condition 1, volume 1, pressure 1. What if we did pressure 2 times volume 2 equals something? And under the same conditions, we would expect this to be also 100. So let's say we increase the pressure to 10. Now the volume is going to decrease to 10 liters atmospheres so that we can get this value. Notice that under these conditions, these two values are equal. So as long as the temperature and the moles don't change from this condition to that condition, then this initial one is equal to this final one. Or sometimes you'll see it P1V1 equals P2V2. This is the more useful expression. I call it before and after. And when you look at a word problem and try and decide, is this a candidate for before and after, you're going to see 3 of these values and one of them's missing. The question is asking for one of those values that's not there. But if it gives you a before and after on 2 of these variables and only a before on one of them, then you can find the after or the final one. And that's what this is trying to show us here. So if we have a gas at 15 liters and 500 millimeters of mercury, a pressure drop to 125 millimeters from 500, then what's going to be the new volume? Right? So when you get a word problem like that, I like to take let's do this. Let's just start from scratch and use this as an example. The final volume of a gas. So we got initial, I'm going to use 1 and 2. 1 and 2. I like to pull information out of the problem and put it in a form that's more compatible with solving a problem. So the initial, or this condition, is pressure is 500 millimeters of mercury. What's the volume under those conditions? 15 liters, right? Okay. Now it wants to know the final pressure. That's the unknown. But what's the under condition? If the pressure, oh, no, it's the final volume, excuse me. It wants to know the final volume if the pressure drops to 125. That's why I like to do it this way, because I can catch my mistakes easier. Now that we have the values in that relationship, we can solve the problem. Right? So if we have P1 V1 equals P2 V2, we can either put the values in and solve for the unknown, or we can go ahead and solve for the unknown now. V2 equals P1 V1 over P2. Now that's all the thinking part. The rest is just number crunching. Put the numbers in the right place. Right? I'm going to leave the units out because it's too crowded. And 125. But we know that millimeters of mercury here and here are going to cancel and leave us with liters. So once we do that calculation, let's see, can I do that in my head? 2 times that is 250, 4. This into 500 is 4, isn't it? Okay, so 4 times 15 is 60, correct? So that's 60 liters. So by dropping the pressure from 500 to 125, a pressure drop of 4 times will increase the volume by a factor of 4. It's this inverse proportion. We decrease the pressure by a factor of 4, we increase the volume by a factor of 4. And there it is. Okay. I got 12 minutes. We get through Boyle's law. I want to try to get through Charles' law too, because I don't want to have a whole lot left over. You want to get through Boyle's because your first experiment is on Boyle's. So you need to know this stuff before we do the lab experiment. And this is a formal lab. So you got to prepare your notebooks for it. Right? Yeah. Be sure I put it out there. Okay. So the units of measure, as long as in this case, think of this as a ratio, right? Ratio. So if there's a ratio between these 2 variables, you can use any unit of measure for pressure you want, right? PSI in this problem, or these 2 can be cubic feet. It doesn't matter, right? Whatever units you use are the units you're going to get at the end. So we're looking for final pressure. It's going to be in PSI. Right? We just solve it for the unknown final pressure, and we plug in our values. And we get 16.24 PSI. pounds per square inch. Okay. That's the relationship of pressure and volume. Now, fast forward about 100 years, I think. To Jacques Charles. That's a Frenchman, obviously. 1787. Did the research, excuse me, but he didn't really publish it. He sent his results to his professional colleagues by letters. And Gay-Lussac was working on chemical reactions and watching the effect that the final volumes of the reaction had. He was interested in the consequences of two gases reacting with one another. What volume would you have at the end, and what pressure would they give you? So he was using Charles' work. So that's why Charles gets credit for it, even though he didn't publish it. Now, the reason that it took 100 years for this particular law to be developed I guess that should have it, because it's his law, is a relationship of volume and temperature. So that means this one, again, has to be constant, and the pressure has to be constant. Right? No problem here or here, but we had to wait for the development of an accurate thermometer, an accurate unit of measure. And that's why Charles' law didn't come along for another 100 years, because we needed to develop the Celsius scale. And then, not only that, we had to take out the negatives. Now, I will say that I think Charles worked before absolute temperature was developed by Kelvin, but he couldn't go very far with it. Because if you have negative values, then this expression, which is Charles' law, if you get to zero, then your whole relationship falls apart again, just like Boyle's. And worse, if it goes negative, that K is worthless, right? But he noticed that as long as he stayed with positive temperatures, that the relationship worked. Okay, so this is what Charles did. He took, this is the way I envision it. How do you maintain constant pressure in a gas? You put a piston in a cylinder and trap the gas. Okay, that makes this constant. And you make the pressure constant by, you want to exceed the atmospheric pressure by just a little bit. So maybe you put a kilogram mass on top. Now the pressure is constant, and that piston can move. So you get a variable volume and a variable temperature. So you need to change the temperature in here also. So one way to do that is to surround it, right, with some container, and then change the temperature in here. And when it comes to equilibrium, then the temperature inside is also that. So maybe ice water or whatever you want to do to control the temperature. And then you measure the temperature and the actual volume. And nowadays we get this relationship, right? As we increase the temperature, the volume increases. And that's a direct proportion. Anytime you get the quotient of two variables equal to a constant, you have a direct proportion. Because if this one goes up, that one's got to go up in order to keep that fraction equal to a constant. So we get the straight line there. Now, what Kelvin did when he came along is, in addition to other things, this is degrees Celsius. So, and this is volume, whatever unit you want to pick. So we get these points here, and we draw a straight line, and we can interpolate within those values, just like we did with our graphing problem. But Kelvin was interested in, he knew the problem here. If you ever got to zero or negative numbers, then that was just blown out of the water. So he wanted a system, not just for this, but for his work in thermodynamics. He wanted a system where you had no negative values for temperature at all. So he wanted to find out where absolute zero was, because there's nothing below that. So he just extended it. Right? So this is the point where volume drops to zero. And that's the only place where you can get, you can't go any smaller than zero volume. So whatever that temperature is the lowest temperature you can get. And he discovered that was minus 273.15, I think, degrees C. So if this is 0K and we go up to zero, then this is going to be 273, positive 273 degrees C. I usually just chop off the 0.15. It's not that significant. Okay, so now we have a Kelvin scale that goes from zero on up. And if you use Kelvin, which we're going to have to do, anytime we solve one of these problems now, we got to change the temperature to Kelvin. Then you don't have to worry about the zeros and negative values. Well, they say 1.6. Okay. So we can also treat Charles' law like we did Boyle's law, before and after. By the same reasoning, if A equals to B and B equals C, then A equals C. And B is our constant. So if we say V1 over T1 equals V2 over T2, that's another expression for Charles' law. It's a before and after situation. Okay, I've got 4 minutes. Let me see if there's anything else we need to talk about here. Solving problems, same way. This is just algebra. Everybody's either taking algebra or in algebra, correct? Okay. Because we're solving for one unknown. Okay, examples. Now, in this case, we've got 50 liters of gas at 25 degrees, and we're going to heat it to 300. Now we want to know what's going to be the final volume. And we have to change the temperature to Kelvin. So 25 degrees would be 25 plus 273, which is 298. And 300 plus 273 is 573 Kelvin. Once we got those values, then we can plug them into our formula and find that the final volume is going to be 96 liters. Now, does that make sense? We went from 25 to 300. Now, the proportion between 25 and 300 is 12. It's 12 times increase in degrees C. But is it 12 times increase for K? No, it's not. We went from 50 liters to 96, which is roughly twice. So for Kelvin temperature, we roughly doubled the temperature, right, from 298 to 573. So we doubled the volume. So that's important to remember. Just because you double, triple, quadruple, quintuple the temperature in Celsius doesn't mean that you're going to get that result in the equation, because you're changing it to Kelvin. And Kelvin is a different ratio. All right, there's another one. I'm going to skip that one. just in the interest of time. All right, no, we're out of time. So we'll pick it up with Avogadro's law on Tuesday. Yeah, I could stick around and finish it, but you guys got to go, and I think it'd be better if we do it face to face. So we'll do this on Tuesday, do a lab on Tuesday, then we'll meet Thursday morning, and you're going to bring me problems, okay? And you can bring them straight out of the review document if you want, any of the review documents or the exams. Right? We can work the exam problems if you want. Now I have to say this to students every semester. Some of them take it to heart and some of them don't. I didn't create that review document just to torture you, because you learn chemistry by solving lots of problems. And the more you can solve, the more comfortable you get with it. So whatever time you have available, try to solve problems in addition to doing the homework. And if you just run out of time, if you don't have enough time or energy, then do every other one, right? Because there's lots of repetition in there. And I think if you take that tactic, if you're able to work more of those problems, I don't think the exams will be such torture. Okay. We're done for today, I think, right? 1:45. We're supposed to call it quits. Okay. We'll pick it up with Avogadro's law on Tuesday. Let me make a note.